In this video, we're going to talk about how to get an exponential equation from a set of data, either in a table, or if you're given 2 points, or if you're given a graph and 2 points are listed with the x and y values. Now, I'm going to show you a technique how to do that using this format, y equals a b to the x. But folks, notice this. There's no transformations here. All right. You see that the x doesn't have anything with it and there's no horizontal asymptote. If you were to write in the hidden 0, the horizontal asymptote would be 0 here. So indeed, whenever you are asked to find the equation given a table, given 2 points, or given a graph that shows 2 points with the horizontal asymptote at y equals 0, yes, you can use this technique that I'm going to review with you in a moment. But if you're given this scenario, if you're given this graph here in the lower right corner, you cannot use that technique. For example, if they gave you 2 points, if they gave you the coordinates of 2 points here, if you use the same technique with this equation, you're going to get the wrong answer. So throughout this video, I'm going to review when you can use this relatively Spartan equation and when you need to use a different mechanism. And the bottom line is, if your horizontal asymptote is not at y equals 0, you need to use an alternative method. Let's now proceed with finding the exponential equation using this table of values. As you can see, the x values progress by +1 each time. Therefore, we can go ahead and use the ratio between the y values to get our b. Specifically, we take this 20, put that over 5, or we put this 80 and put that over 20, or we put this 320 and put it over 80, and we get the same value, which is 4. Therefore, that is going to be our base. So we now know that this function is going to be y equals a times 4 to the x. At this point, we proceed to go ahead and just plug in any point. Let's do 0 for x. That'll be the easiest. So now we'll have y equals a times 4 to the 0 power, but our y value for that would be 5. So I'm using, folks, this first point right there, 0, 5. And when we do that, we find that this goes to 1. A is going to equal 5, and therefore our final function is going to be y equals 5 times 4 to the x. Again, as I alluded to in the opening of this video, the HA is 0 and there's no transformation. Now, suppose you're given a table that doesn't march like this with mathematical precision or in apple pie order, and you basically are just given 2 random points. Okay, let's say you're given the points 1, 20 and 0, 5. All right. So no table is given to you. You can't get that b value the way I just showed you. Well, the way you would proceed here is by using what's called division of equations. So you're going to set up 2 equations and then you're going to divide them. So the first equation is going to be 20 equals a times b to the first power. So all I did here, folks, was just plug in the 1 for x and 20 for the y. Similarly, we're going to get 5 equals a times b to the 0 power. And now what we're going to do is we literally are going to divide these equations. So we are allowed to do the following. Take this equation, put a line, and then bring this first equation and bring it right beneath it. like so. Now when we do that, the a's cancel out. So we're going to have like so. And then we're going to have 1 over 4 equals 1 over b. If we cross multiply, we're going to get b equals 4, which is the same result we got when we did it using the table method. Now it's a matter of just plugging b equals 4 into one of these equations to get our a. So let's use the top one. 5 equals a times 4 to the 0 power. And we're going to get 5 equals a. And we're going to rebuild our equation to get 5 times 4 to the x power, which is the same result that we had a few moments ago. Again, no transformation and no horizontal asymptote. Next, we are given this graph and given two definitive points, and we're asked to find the equation of this exponential function. Folks, look, the horizontal asymptote is at y equals 0. That's a big bonus. When we have that, we are allowed to use the same technique we did moments before. If you don't have the horizontal asymptote at y equals 0, you cannot use the technique I'm about to show you. Okay, so let's build our two equations. Here's 250 is going to equal a times b to the 3rd power. Okay, again, all I did was substitute that for x and this for y. And our second equation down here is going to be 50 equals a times b to the 2nd power. We literally are going to divide these two equations. The a's are going to cancel out. We're going to get 5 equals b. Once we have 5 equals b, we can go ahead and plug it into either equation. Let's use this one. 50 equals a. Now we have b to the 2nd power. 50 equals a times 25. A equals 2. Our final answer, folks, here in green is y equals 2 times 5 to the x power. Again, no shift left or right, and no horizontal asymptote other than y equals 0. In this next example, we are asked to find the equation of this exponential function. But folks, notice, look at our horizontal asymptote. It's at y equals 2. They give us 2 points. So let me show you how using the previous technique will not give us the right answer. All right, let's go ahead and take these 2 points, 4, 4 and 5, 8. And we're going to use the technique of division by division of equations, and I'm going to show you how the answer that we get is not the same graph. Okay, so there's our first equation. Here's our second one. We are now going to divide these equations. We're going to cancel out our a's, and we're going to get 2 equals b to the 1st. We're then going to plug in 2 for b, and let's use the original bottom equation. So we're going to have 4 equals a times 2 to the 4th. Okay, that's using the fact that we have b, and we're using x equals 4 and y equals 4. We're going to get 4 equals a times 16, which is 2 to the 4th power, and a is going to end up being 1/4. So our final equation, folks, down here in green is going to be y equals 1/4, which is our a value, times 2 to the x power. Okay. Let's go ahead now and show you that on Desmos. Okay. Right there. Not even close. Okay, so that technique failed to match that original red graph. And you may say, okay, well, how about we just add the +2 horizontal asymptote? That would give us that second red graph. Let me take, I guess I can't, we got two red graphs, but anyway, this one here, the original red goes through 4, 4, 5, comma 8. The second one would be this equation down here. The bottom line, folks, is you cannot use that technique whenever you are dealing with a graph that has a horizontal asymptote other than y equals 0. So now I'm going to come back and show you how to get the equation of this graph with the horizontal asymptote at y equals 2. Okay, I've recreated that graph on my chalkboard. And folks, we're going to use this transformation equation right here. A times b to the x minus h plus k. And you could see that our plus k, that's going to be our horizontal asymptote. So we initially have that. And I'm going to call the point closest to the horizontal asymptote Roman numeral 1, and the other point further away Roman numeral 2. The way this works is we're going to use Roman numeral 1, that point, to find our a value and to find our exponent here, whether we're going to have minus h or plus h. And we already have the k value, that is the horizontal asymptote. And then we're going to use Roman numeral 2 to find our b value, and we will have everything we need to complete that yellow equation. Okay, so let me show you how to use point 1 to our advantage. Folks, you go to the horizontal asymptote. Okay, you start at the horizontal asymptote. And you go from the horizontal asymptote to the point Roman numeral 1. And you mark that distance. So here, the y value at the horizontal asymptote is positive 2. You go up to positive 4, that's the y value of Roman numeral 1. That distance is positive 2. So indeed, our a value is going to equal positive 2. And that makes sense, because having a positive a value means your function is not going to be flipped over the horizontal asymptote. Okay, now, to settle this exponent here, this x minus h, notice in this formula you have a minus h. And in math, when you have a minus in the formula, it means do the opposite. We've seen that in the vertex equation as well. So folks, to get your exponent straightened out, your horizontal transformation straightened out, you go to the y-axis and you move from the y-axis to Roman numeral 1, and you note how far in the x direction you went. You went from x equals 0, which is the y-axis, to point number 1, you moved positive 4 in the positive, you move 4 in the positive direction. You're going to rename that as minus 4. So our exponent is going to be x minus 4. Okay, so we've extracted everything we need from the horizontal asymptote and from Roman numeral point 1. Now we're going to move to Roman numeral point 2. So let's write down what we have so far in yellow. We have y equals positive 2. That's our a value. B, we do not know what that is. Raised to the x minus 4 power plus 2. Okay, now what we're going to do is simply plug in Roman numeral 2, which is 5 comma 8 for x and y, and we are going to solve for b. So here in white, we're going to have the y value is 8. We're just going to plug that right in on the left side of that equal sign. 2 times b, we don't know what that is. X is going to be 5 minus 4 and then plus 2. So we're going to have 8 equals 2 times b to the first plus 2. We're going to end up with 3 equals b to the first power. Folks, we have everything we need. So I'm going to reconstruct this final equation up top in green. We now have y equals positive 2 times the base is 3. Our transformation is x minus 4 within the exponent plus 2. This is our final equation. Looks nothing like what we got when we just used those 2 points. All right, let's go back to Desmos and confirm that. And here it is. Here's our equation that we got, and that is the equation with the horizontal asymptote at 2 and these 2 points. And again, at the risk of being repetitive, that's the graph that we got using division of equations by itself. And the other thing I did was, I went to Mathway and I compared this equation up here to this equation. I put an equal sign between them and asked Mathway to verify the identity, and they said they are not the same. Again, to repeat, you cannot use division of equations when the horizontal asymptote is anything except for y equals 0. In this next example, we are given this decay function. You could see as you move left to right, the graph heads towards the horizontal asymptote. So we know that b is going to be some sort of fraction between 0 or 1. Remember, has to be positive. Can't be 1, can't be 0. Okay, we see that our horizontal asymptote is at y equals 3. We cannot use division of equations. So we're going to use our Roman numeral points technique. At Roman numeral 1, we're first going to get our a value. We're going to get on the horizontal asymptote at y equals 3. We're going to move toward point number 1. That's a movement of positive 5. Because there's no negative in front of that a, we're going to write down exactly what we see for our a value. So our movement for a goes from 3 to 8. That's plus 5. That's our a value, positive 5. Now, notice there's a shift to the left. So if you're at the y-axis and you move to Roman numeral 1, you move 1 in the negative direction, like so. Because there's a negative in that formula, we're going to say that our exponent is going to be x plus 1, the opposite of what we see. Again, you get on the y-axis, you move to point Roman numeral 1. What did you do? You moved 1 in the negative direction. We're going to flip that to positive because of that negative in the parent equation. Finally, our plus k, that means we're going to write what we see for the vertical transformation. We see a plus 3. That's what we're going to use. All right, so armed with this information, we are now going to move to point 2 to get our b value. So we're going to have y equals positive 5, which is our a value, times b, we don't know what that is, raised to the x plus 1, and then a vertical transformation due to the horizontal asymptote of plus 3. We're now going to plug in, folks, the point negative 2, comma 13, otherwise known as Roman numeral 2. So we're going to have our y value is 13, 5 times b, which we don't know. Our x is negative 2 plus 1, and then plus 3. 13 equals 5 times b to the negative first power plus 3. That's going to give us, eventually, we're going to bring this 3 to the other side, make this 10, and then we're going to divide by 5. So we're going to get 2 equals b to the negative 1, and we're going to flip that, b equals 1/2, And that makes total sense, folks, because as we predicted at the outset, b was going to be a fraction. And we also know that the positive a value makes sense because this graph is not flipped over the horizontal asymptote. Folks, our final answer for this particular function is 5 times 1/2 raised to the x plus 1 power plus 3. Right up here in green, up in the corner. Let's now revisit the graph that we saw earlier in this video, shown here with a horizontal asymptote at y equals 0. Recall, because the HA was at y equals 0, we're allowed to use the division of equations method, and we obtained this function in the blue rectangle as our final answer. Folks, let's now go ahead and use the second technique in evaluating a graph, namely the Roman numeral 1 and 2 points. Recall, we are going to use this transformation equation, and we're going to fit in from point 1 the a value. We're going to elucidate the exponent, and the k value is going to come from the horizontal asymptote, which in this case is 0. Okay, let's first get our a value. We go to the horizontal asymptote and we move to Roman numeral 1. In doing so, because the y value at Roman numeral 1 is 50, we're going to move in the plus 50 direction. So that is going to be our a value. To get the exponent elucidated, we're going to start at the y-axis and we're going to move to point number 1, and we're going to note how far in the x direction we went and whether we went to the right or to the left. And indeed, we went to the right 2 units. Because of that minus in that parent equation, we're going to use x minus 2 as the exponent. And then finally, as mentioned, our k value is going to be 0. Okay, let's write what we have so far. We have y equals positive 50 as our a value. B, we do not know what that is. And we're going to have x minus 2 in our exponent. And plus 0 is the horizontal asymptote, so I'm going to leave that blank. Okay, at this point, we're going to bring in Roman numeral 2, which is 3 comma 250. And we're going to plug in x equals 3 and y equals 250. That's going to give us 250. Let me redo that. 250 is going to equal 50 times b, we don't know what that is, to the x minus 2. And my apologies, we're going to plug in x equals 3 there. So that's going to become 3 minus 2. 250 equals 50 times b. Therefore, b is going to equal 5. So our final equation, using the point 1 and point 2 technique, is going to be y equals 50 times a b value of 5 to the x minus 2. Now, you may say to yourself, wait a minute, these don't match. All right, well, let's see if they do. Let's see if we set 2 times 5 to the x, which is what we got from dividing equations, equal to 50 times 5 to the x minus 2, let's see where that algebra takes us. Well, immediately this 2 is going to cancel, and that's going to become 25. So we're going to have 5 to the x equals 25 times 5 to the x minus 2. Now, folks, we can rewrite this as 25 times 5 to the x times 5 to the minus 2. Recall when you're multiplying and the bases are the same, you keep the base and you add the exponents. When we do that, 5 to the negative 2 is indeed 1 over 25. So I'm going to erase this and put that in the denominator of 25. And when we do that, the 25s cancel out, and we get 5 to the x equals 5 to the x. So when you're doing these problems, be careful. Don't immediately jump to the conclusion that we got a different answer. Go through the machinations, do the algebraic manipulation. And once again, I checked on Mathway. I set these two equal to each other, and Mathway did indeed verify this identity. Folks, in this next example, we see that our horizontal asymptote is not at y equals 0. Therefore, we're going to use our Roman numeral 1 and Roman numeral 2 technique. However, it's very important to recognize, folks, that that is going to be our Roman numeral 1, and this one is going to be number 2 because this is closer to the horizontal asymptote. Let's go ahead and find our a value first. Our a value is going to be the y distance and direction from the horizontal asymptote to the first point. So you can see we start out at y equals 4 and we go down to y equals positive 2. That's a movement of minus 2. And that's going to be our a value. And it does make sense that this is a negative because you could see our graph is flipped. Our graph is going to be a decay function that approaches the horizontal asymptote from beneath. That's indicative of a reflection over the HA. Let's now go ahead and elucidate the exponent, and we see that Roman numeral 1 has no shift right or left, so our h value is going to be 0. So we know that we're going to have negative 2b to the x plus 0, and our k value is going to be our horizontal asymptote, which is plus 4. So let me rewrite this. This is very messy. So our a value is negative 2, b to the x plus 4. Okay, now we're going to use Roman numeral 2, which again is further from the horizontal asymptote, to get our b value. And we know our b value is going to be a fraction less than 1 because this is a decay function that approaches the HA from beneath. Okay, so we're going to plug in our Roman numeral 2. Our y value is negative 4, is going to equal negative 2b to the negative 1 power, that's our x, plus 4. That's going to give us negative 8 equals negative 2 times b to the negative 1. We're going to divide both sides by negative 2, and we're going to get 4 equals b to the negative 1. Therefore, b equals 1/4. And again, we did anticipate that fraction. So our final answer, folks, is going to be, here in green, y equals negative 2b to the x, negative 2 times 1/4 to the x power plus 4. And again, the negative makes sense. The 1/4 fits a decay function. There's our horizontal asymptote. In this next example, we have a exponential function with a horizontal asymptote at y equals positive 6. Therefore, we're going to use our Roman numeral 1 and 2 method. Roman numeral 1 is always closer to the horizontal asymptote. Folks, we have here, as you move left to right, a graph that goes away from the horizontal asymptote. That means this is a growth function. We expect this b value to be greater than 1. However, we expect that a value to be negative because this graph is flipped over the horizontal asymptote. Let's use point number 1 to get our a value. We start at the horizontal asymptote, which is at plus 6. We're moving down to plus 3 for a y value. That means we move minus 3 in the vertical direction. In terms of the exponent, the x minus h component of this transformation equation, we do not move left or right. So our h value is going to be 0. Finally, our k value is the horizontal asymptote, so that's plus 6. So far, using point 1 alone, we're going to have y equals negative 3. B, we don't have that yet. X, the h value is 0, so it's only x, plus 6. We're now going to plug in Roman numeral 2 to get our b value. And whenever I have 6 and b in the same equation or expression, I put a little tail on that b to differentiate it from the 6. Okay, our y value is 0, and we're going to have negative 3 times b to the 1/4 power, that's 0.25, plus 6. Okay, we're going to move this to the opposite side of the equation. We're going to get negative 6. We're going to divide by negative 3, so we're going to get 2 equals b to the 1/4 power. In order to solve for b, we're going to raise both sides of the equation to the 4th power, and we're going to get b equals 2 to the 4th, otherwise known as 16. So folks, our final expression, or our final equation, written over here in red on the left, is going to be y equals negative 3 times 16 to the x plus 6. And again, the negative fits out front because we've got to flip over the horizontal asymptote. 16 is greater than 1. That's a growth function.